Good morning, students. In this lecture, we will see few more typical examples of inverse Z transform. In that, first one is find the inverse Z transform of x of z equal to log of 1 divided by 1 minus az inverse, where the ROC is magnitude of z greater than a. In this sense, while calculating inverse Z transform, the extracted x of n has to be right sided. So let us start solving for inverse Z transform. Let us write x of z is equal to log of 1 divided by 1 minus a z inverse. This can be written as minus log of 1 minus a z inverse. Now this is in the form of log of 1 minus x type, and which is expanded with the help of power series as I can write log of 1 minus x, which is equal to minus summation n ranging from 1 to infinity x raised to n divided by n, where x is less than magnitude of x less than 1. Now this we will compare with x of z that is equal to minus this minus it is, and there is one more minus now, that is minus of summation n ranging from 1 to infinity x is a z inverse raised to n divided by n, and our x is again a z inverse which is less than 1, and therefore I can write magnitude of z greater than magnitude of a, which is expected. Now this we will solve it as summation n ranging from 1 to infinity a raised to n divided by n into z raised to minus n. Now when I compare this with the equation, standard equation of our Z transform, n ranging from 1 to infinity x of n z raised to minus n, like this, we can extract, or I can say taking inverse Z transform of this equation, I will write it as x of n equal to a raised to n divided by n, for n greater than or equal to 1, and it is 0, I can say otherwise for n not greater than or equal to 1, and this is the inverse Z transform of x of n. Or I can write x of n as a raised to n divided by n into u of n minus 1. So for n minus 1, n equal to 1 onwards, we will have x of n as a raised to n by n. Now in the similar way, let us take the one more example, that is x of z equal to, I can write log of 1 divided by 1 minus a inverse z, wherein magnitude of z less than magnitude of a. In this sense, the x of n which has to be extracted, that has to be left sided, that is indicated by this ROC, and therefore the same x of z we will write it as minus log of 1 minus a inverse z, And as usual, using the power series expansion method, we will write it as minus of minus summation n ranging from 1 to infinity, a inverse z raised to n divided by n, and where a inverse z is less than 1, or I can say magnitude of z less than magnitude of a, which indicates it is a left-sided sequence. Now when I want to compare this with the standard equation, I need n value negative, so I will put n is equal to minus m in this case, and hence I will write it as summation m ranging from minus 1 to minus infinity a inverse z raised to minus m divided by minus m, and that is equal to I can write summation minus 1 to minus infinity minus I will write this as a raised to m divided by m into z raised to minus m. And when again this is compared with the standard definition of Z transform, this is my x of n. X of n is minus a raised to m divided by m, and the range is from minus 1 to minus infinity, indicating that it is left-sided signal. So I say here taking IZT on both sides, I can write x of n is equal to minus a raised to m divided by m, that is I can say u of minus n minus 1, that is nothing but the range of summation. Or I can write this as x of n is equal to, sorry, here it has to be m, so that I can write all m has been replaced by n, so I will write it as minus a raised to n divided by n, in which is present for n less than or equal to 1, and it is 0 elsewhere or otherwise. Or I can write the same equation in the form of like a raised to minus a raised to n divided by n into u of minus n minus 1. So this is the inverse Z transform of log of 1 divided by 1 minus a inverse z. Now similarly, one more typical example let us take, that is x of z is equal to e raised to 1 upon z. Now in the last in one of the lectures we have seen either we can write e raised to x formula for this, or there is one more method to solve such examples is taking log on both sides. I can cancel this exponential term. So if I take log on both sides, I will write log to the base e x of z, which is equal to 1 upon z. Now if I differentiate this, it will be 1 upon x of z into d by dz of x of z, which is equal to minus 1 divided by z square after differentiating. Now I can, this x of z I can take it on this side and this minus, so that I will try to write this in the form of differentiation property. So this minus I will take it on left hand side and multiply, or 1z I can take on this side. So minus z d by dz of x of z, which is equal to, I can write z inverse, there is one z which is remaining here, that z into this left hand side x of z I will transfer it to right hand side. Now in this case, taking again inverse Z transform on both sides, we will be able to write this. We know that using the property of Z transform, it is n into x of n, and this is nothing but x of n minus 1, and therefore I can write x of n is equal to 1 upon n into x of n minus 1. This is the way how to solve inverse Z transform of such exponential functions. So similarly, we can have different approaches to solve different type of examples or different type of signals while calculating inverse Z transform. Now again, if you want to go with different values of this x of n, or initial value of this x of n, and also n equal to 1, 2, 3 and so on. Now this is in general in the form of x of n minus 1. Actual samples and hence the generalized equation, if you want to find out, try to find out first the initial value as x of 0, which is nothing but limit z tending to infinity x of z, and that is nothing but here limit z tending to infinity, it is e raised to 1 upon z, and that is equal to, I can say, e raised to 0, which is equal to 1. So what does it mean here? At n equal to 0, the initial value of the sequence, I have calculated it as 1. So similarly, if I am trying to calculate 1x of 1, putting at n equal to 1, that is for n equal to 1, then x of 1 is nothing but, it is 1 upon 1 from this equation, that is x of 0. So which is nothing but x of 0 is 1, and hence it is again the answer is 1. Now for n equal to 2 here, I will write x of 2, that is 1 upon 2 here, 1 upon 2, and it is x of 2 minus 1 is 1, and that is nothing but 1 upon 2 here, 1 upon 2. And similarly, when I put n equal to 3, I will get x of 3, this is 1 upon 3, and then 3 minus 1 is 2, so it is x of 2. So 1 upon 3 into 1 upon 2 is 1 upon 6. And if you observe, while putting different values of n from 1, 2, 3, 4 and so on, we observe that here at n equal to 1, this I can write it as 1 upon 1 factorial, this is 1 upon 2 factorial, this is 1 upon 3 factorial. Similarly, when I put n equal to 4, this becomes x of 4, then it is 1 divided by n is 1 upon 4, and this is x of 3, that is 1 upon 4 into 1 upon 6, and that is nothing but 1 by, I can say, 24, and that is nothing but 1 upon 4 factorial. So now in general, for different values of n, I can write x of n as 1 upon n factorial u of n. This is actual, I can say, time domain signal for the x of z, that is e raised to 1 upon x. So we will stop here, and in the next class we will see how to solve the difference equation, that is system described by the difference equation using Z transforms. Thank you.